This video is about zeros and their multiplicities in the context of polynomial functions. We're going to start our notes with the zeros theorem, which states this: every polynomial of degree n being greater than or equal to 1, has exactly n zeros, provided that a zero of multiplicity k is counted k times. For example, as we've seen with multiplicity, if I had a root that showed up as the factor x minus 2 in the polynomial, but let's say that x minus 2 was squared, what this theorem states is we're going to count that as two roots since it's squared. And if we do, then we can match the number of roots exactly with the degree of the polynomial. Let's try an example where we want to factor the following polynomial completely and find all its zeros. State the multiplicity of each zero. Our polynomial reads f of x equals x to the fifth plus 16x cubed plus 64x. Now we're going to start by just using our basic or old trusted and true factoring methods from algebra. And in other words, we're going to look for a greatest common factor and then apply any other tricks we have. For this given function, there is a greatest common factor of x, and if we factor the x out of all terms, that leaves us with x to the fourth plus 16x squared plus 64. Now we'll try to continue factoring this three-term trinomial that's left over, the x to the fourth plus 16x squared plus 64, and you'll recall there are ways to get through this. It's quadratic in form. It's not exactly quadratic, but the way to get around that would be to use possibly a substitution. So we'll say let u, usually the letter u is used for this, let u equal x squared. That's the variable in our middle term. And then we're going to rewrite this using the substitution. So we'll say this is really x times, and then if we use the substitution where u is x squared, then we really have u squared plus 16u plus 64. After doing our substitution here, we'll go ahead and keep factoring, and u, the letter u here, is going to help us get through that. We can now take this trinomial, which is u squared plus 16u plus 64, and factor that as a trinomial. In fact, this would just be a u plus 8 all squared. That's what we call a perfect square. And then, of course, when using substitution like this, we now have to go put the substitution back in place. We don't want the letter u in our answer. We just use that temporarily. And so we'll rewrite this as x times, and then in place of u, I'm going to write x squared plus 8, and that's all still squared. Okay, so now this is the factored form of our original polynomial. We want to be able to find all of its zeros. Well, the first factor we have, which is just an x, is hopefully clearly giving us a 0. We can set, remember, each of these factors to 0, so x would equal 0, that's a 0. But then this second factor, the x squared plus 8, if I wrote that equal to 0, I'd have x squared plus 8 equals 0. You'll recall or notice fairly quickly that this is going to produce some imaginary solutions. That's fine. And we'll write this as x squared equals negative 8, which would mean if I take the square root of both sides of this equation, x equals plus or minus. Now the negative is going to pop out as an I, and then 8 under a root can be reduced to 2 root 2. And so we have 0 as a root, or a 0, and we have now these other imaginary zeros as well. Let's go ahead and use the zeros we've found so far to continue and factor this original polynomial more completely here. So we're going to keep the x we had there originally at our previous step, but now what we just did was take the x squared plus 8 factor, which normally is not factorable according to the old methods, but we found the imaginary zeros that would show up in solving that. And so what we're going to do is force factor it in this way. I'm going to keep some brackets here holding what used to be the x squared plus 8. But now what we're saying is that x squared plus 8 could be factored using these zeros in the following way. X plus I times 2 root 2 times x minus I times 2 root 2. In other words, these factors are coming directly from the zeros we just found in solving that equation. Let's not forget where this is all coming here from. So in the previous step we had x squared plus 8. We just forced that into a factored form, which includes the x plus I to root 2 and x minus I root 2 root 2. And by the way, to check that, to verify, if you don't believe me, go ahead and FOIL these together. See if you don't get x squared plus 8 for the result. Those are equivalent. So let's also not forget that that factor, the x squared plus 8, had the power of 2 outside. We better keep that. So there's really a power of 2 outside these brackets that we've been using here now. And then using exponent rules, that really means, since we're multiplying these two factors together, that this power of 2 would apply to each of these factors inside. So in summary, let's keep all this going. We have x, then really we have x plus I to root 2 squared, and then x minus I to root 2 squared as the complete factored form of our original polynomial. Now this will help us understand the multiplicity as well. So if you go back and look through each root, notice the root we already spotted as 0, where x equals 0, came from the factor of just the plain x we had way out front. The power of that x was only a 1, that wasn't even visible, which means the multiplicity of that 0 is 1. And then if we go to the other two zeros we'd found, the plus or minus I to root 2, you'll notice where they come from in the factored form were these second two factors, but each of those factors has a power of 2 with it, which means the multiplicity for both of those roots, the plus and the minus, are each 2. And so that does it. We have now the total factored form and the multiplicity of each of our zeros.